self-assembly process where we might produce something. To do this, IBM, they used scanning tunneling microscope, which took them a fair while to do. But what we'd like is for some way to get our nanoparticles or molecules to organise themselves. Does that seem unreasonable?
In a significant move forward, in March we're creating electronic circuits that are thousands of times smaller than today's most advanced technology. IBM is announcing a milestone in the ability to manipulate and understand matter at the atomic level. Scientists at IBM's Olivet Research Center in San Jose, California have for the first time demonstrated the ability to measure exactly how much force is needed to move individual atoms. Knowing the different forces required to move different atoms will allow IBM's nanoconstructionists to figure out which materials should be used for building devices from the atom up. For example, the so-called sticky atom will be used for something that you don't want to move, like a vase that you want to keep in one place. While a so-called slippery atom would be used when you want to build something like an on-off switch that needs to move with ease.
10 or 20 years ago, nobody could imagine that we would have today laptops, cell phones, and iPods. I think it's impossible to speculate what nanoelectronics will bring us in 10 or 20 years, but I'm sure it will change our world even more than the iPods we have today.
The force is measured via tiny changes in the frequency of a small quartz tuning fork. This exploration of the realm of atomic-scale structures and devices stands to impact the future direction of information technology. This is Jeff Gluck reporting.
So that's how they move those atoms. But we want these self-assembly things to happen, which we'll come back to in a second. Another way is electron beam lithography, where we use an electron beam to either directly write information or to use projection lithography. For example, to make nano circuits. Our problem is this. This is the processing time. This is the processing time to produce a 5 by 5 millimetre square silicon wafer for the area. And if we have a look at photolithography, it takes very little time, but the scale is very large. So this is the resolution in angstroms. If I want to get down to E-beam lithography here, we're talking maybe 25 hours. And as I get down and down, smaller and smaller in resolution, you can see 30 years for AFM lithography, STM lithography, and that up to 3 billion years, which is what we were talking about before, the lifetime of the universe. So it's a serious problem to use these sorts of techniques for that. But self-assembly is not that unreasonable. We are all examples of self-assembly. So what people are trying to do is mimic nature in trying to develop materials that self-assemble themselves. And that's what that story about the nanobots was on about earlier. They will have to self-assemble. And the problem is, if you read the science fiction, is that how can we control the self-assembly, and also they'll have to reproduce themselves. So they'll self-assemble and then make more and more and more. How do we control that? And that's the story of Grey Goo and the taking the world. So the self-assembly isn't too difficult. Here's an example of some self-assembly nanotubes. We can look at perhaps a simple demonstration. How they decide to join together depends on what we're doing here. We're just if I put them self-assembly process. These are a bit squashed. They've got a bit squashed. You can see they'll eventually self-assemble. And in fact, they self-assemble. This, if I have them all the same size, I use this as an example of forming a close-packed plane in crystals. They'll form a close-packed system. So you can see that we can get this self-assembly. In this case, it's just static electricity that's causing that self-assembly. But for our purposes, what they're interested in is some sort of chemical or biological self-assembly that's going on. So here's some examples. I'm not going to go through all this information, but just to show you that here's some self-assembly. We've got these nanomagnets and a self-assembled polymer mask. So again, they can produce these the data storage, have a nanoporous template, and the nanomagnetic material forms in that porous material. We can have anodized aluminium oxide templates. Again, we can do anodization and form these sorts of structures. We'll talk about in a minute. And get this. And so on. So self-assembly is very important, and it needs a lot more research done on this self-assembly. So I'm going to talk a little bit about nanocoatings. Why would we want to do nanocoatings? Well, coatings have been around a long time, for example, for corrosion resistance. So you might have, if you've got a slightly older car, a chrome plated bumper bar. So the bumper bar's made out of mild steel. I plate it with chrome, it looks pretty, but it also protects the steel from corrosion. I may have other applications where I need a hardware-resistant surface. Usually hardware-resistant surface means a hard material, which means a brittle material. So we don't want it to break, we just coat the surface of ductile metal with a hard metal or a hard ceramic. Other applications, such as in engines these days, if I want to run at higher temperatures, I coat the metal lining, the metal cylinder or the top of the metal piston with a ceramic coating. We're doing all these different things. So why put coatings on? All sorts of reasons here. Optical properties, smart window coatings, those sorts of things, wear resistance, a whole range of things we could look at. Why do nanocoatings? Well, we just said that nanomaterials have much different properties than normal materials. So if we put nanocoatings on, we find that we may get much better properties. We also find that nanocoatings, because they're very thin, behave quite differently to simply mechanical. So think about our discussion so far about nano things. They have unique properties. So I'm just going to give a couple of examples of some research reports. In this case, we have nanoscale hydroxyapatite coatings on titanium substrates. Why did we do that? Well, it's for biomedical application. And what we wanted to do is inhibit wear, reduce corrosion, and promote biocompatibility. Titanium, while it's very good, it will still corrode in the body. And it's also very hard to get bone to stick to it. So the concept was that if we put hydroxyapatite coating on the surface of the titanium and it was porous, the bone could grow into the coating and hold the inflammatory pus. The other application was to inhibit wear. We were thinking of replacement knee joint where we've got the bone rubbing on bone, and if we have metal on metal, that's not very good either. So we coat it with zirconia, which has fairly good wear resistance. And I'm just going to talk about hydroxyapatite. So this is the applications that we're interested in. We use the sol gel coating. Now sol gel coatings are very good. They're a nano thing, I guess. We have nanoparticles in the sol gel. And the advantage was low production temperatures. Remember we said nanoparticles. we melt at much lower temperatures. In this case, we're going to sinter them, and we can sinter at low temperatures. Why is that important? Titanium goes through a phase change at about 450 degrees. So we wanted to keep below that. So we have to use nanoparticles. And because we're using a salt gel, it's a liquid, we can essentially take our piece of metal, dip it into the solution and pull it back out. So we get very good even coating on the surface. The problem is, when you do coatings, you've got to make sure that the coating you've got on the top is compatible with the metal underneath. In this case, it's not going to be. So what we did, we took the titanium and we anodized it. So we got a titanium dioxide layer on the surface, which is a ceramic. So we should be able to bond the ceramic to a ceramic. The bonding here is very good. The bonding here, we were worried about. We also played around with a phosphate layer here as well. And simply we got the titanium, we anodized it at different voltages, and then we coated it. Our coatings of the titanium were 50 to 150 nanometers. We don't worry about the phosphating. And we did this process here where we spin coated for 20 seconds and then we did the heat treatment to get our final product. We then did some mechanical testing. This is the specimen here. We did some X-ray diffraction and we showed that there wasn't a big change in phases. This is the hydroxyapatite peaks, this is the titanium peaks. And we saw that, we saw that we got some increases depending on, this is 75 volts, this is 50, and this is 25 volts. And we could measure the interfacial fracture energy. So we showed that, yeah, we can control the properties, and the properties were pretty good. This is the fracture toughness of the coatings again. The fracture toughness of the anodized layer is up here somewhere. So we know any failure is due to these levels here. And these are just some microstructures. So it worked very well. We also use this technique for corrosion protection. A company in Australia was interested in coating in, they make hot water tanks, and they wanted something besides glass. So they were using salt gel techniques to coat that. The interesting thing is, and you've got to take this into account when you do these coatings, is that you've got to match things up. The crystal structure, we found that we really wanted annotators because one of its crystal sizes was about 9.5 angstroms, which compared favourably with hydroxyapatite. So we didn't get crystal strain mismatch. We also found that thermal expansion, we're going to heat this thing up to 400 degrees and then let it cool down. If the layers have different thermal expansions, we're going to get cracking. And again, we found that the titanium's 8.9, annotators is 10.2, and hydroxyapatite 16.9. So we had this, what people these days call functional gradient system. If we had a lot of rutile, we'd have a problem. Because the thermal expansion doesn't nicely increase across the width of our interface. Now these are just some fractures. Other coatings, some work done at UTS is using nano gold to coat glass surfaces. And here you can see, can't read these graphs very well, sorry about that. But this is a standard tinted glass, and you get about 50% transmission of heat. With the gold one, white, 50% white. Here you get about 77% white, but you keep out a lot of the thermal energy using gold. It sounds like it's going to be expensive, but it's not. because it's only nanometers thick.